So, welcome to the Data-Driven Breeding and Genetics. My name is Tiago de Paulo Oliveira. I am a biostatistician at the Roslin Institute, and I'm working in the Highlander Lab with quantitative genetics since October 2020. Thank you for coming today. And in this first lecture, I will introduce the grammar of graphics, and that was introduced by Leland Wilkinson, and then said by Hadley Wickham, who translated that idea into the ggplot package. This package is the most famous and important package for plots in R. So today we will talk about different things. I will start with introducing how install all the update packages in R, and then we go through the idea of ggplot2, the grammar of graphics, passing for all, the constituents of a plot, like data, mapping up to themes, and then we will talk a bit about the ggplot, the quick plot, and go to annotation, how make plot composition, and then they have references and some useful links I've been using here. So to install a package in R is very straightforward and easy. First of all, you have two main ways to install packages. You can use the install packages function, including the name of the package you want to install between the quotations marks. If you want to install more than one, you should use the concatenate function, as you can see here. These packages are directly installed using the version available on the CRAN. Another way is installing packages directly from GitHub, and then this is the version under development. You can use the function install GitHub from the DevTools package. You can also remove packages, and for that you can use the remove packages function, including the name of the package you want to remove between the quotation marks. You can also load packages, and this is another straightforward way. If you want to load just one package, you can call the function library or require, and then put the name of the package between quotation marks. However, if you want to load more than one at once, you can store the packages you wish to load in like a vector of characters. Thus, you can use the apply function from the apply family to load all the packages. And so in this case, I'm using visible function because I don't want to see the output of this load. You can also unload the package using the function detached. In this case, I'm detaching the ggplot2 package from the console. You can, there's some ways to update packages. In this particular case, I'm showing how to update alphas in R, and then for that I'm using the update package function. It's straightforward. Here we can apply the same logic as before. To update multiple packages at once, we can store the characters, the name of the packages in a vector of characters. And then we can use this vector in the updated package function using the argument old package equal to pkg. You can also update all packages at once, and this. But I recommend you use the ask equal false, because if not included, then R will ask you if you want to update the package for each package you are updating. So, for example, if you have 15 packages to be updated, then R will ask you 15 times, oh, do you want to update this package? And then you have to say yes. And then they will ask again, do you want to update that package? You have to say yes again, basically. So, after understanding the basic concepts on how install, load and unload and update packages in R. We may start talking about the grammar of graphics, and I hope you will be able to understand a bit more about basics of grammar, of graphics, the basic commands and arguments in ggplot2. And in the end of this lecture, I think you may able to understand how ggplot works, and I have some data sets I will use as example in this lecture, and based on that examples, we can build some nice plots and understand how the main arguments of the layer, themes, and annotation works. So the grammar of graphics, grammar is a basic element that make up an area of knowledge or skill. So as definition, it's the grammar of graphics. The grammar is the building blocks that allow us to communicate and describe a particular knowledge. And Hadley Wickham has been improving the work of Leland Wilkinson and programmed this excellent package called ggplot2 that make our life much more easy to make a plot and get some visualization that we want. And today we will see how to use it and create powerful visualizations. We can provide a strong foundation for understanding the diverse range of graphics, and we can also decompose graphics into its constituents. There are different paths to a graphic, like their data, mapping, facets, scales, statistics, geometries, coordinates, and themes. We will go through each of these components over this lecture. The power of the grammar shall be the illustrated over this course. So in this slide, I'm illustrating the relationship between these components. This illustration shows how all of these components are related. For example, data is directly related to mapping, scales, and facets, while mapping and scales pass some information to a statistics component. On the other hand, theme is completely disconnected of all components, and it makes sense because theme doesn't depend on that component, doesn't depend on data. The great idea behind grammar of graphics is that it can be applied to anything, and you can do whatever graphic you want to make. This is a very flexible idea, and it's a very flexible package. So the data is the most important component in the way that turns an abstract plot in a concrete plot. Without data, we have just a blank plot, right? And then without data, we don't have a visualization of anything. One important point is to operate the grammar correctly. We kind of require a tight data format, and we will talk more about this format in the next lecture. For now, I am assuming the data I'm using here is an off-tied. The data sets are generally is stored as data frame or table, and the table format comes from the tidyverse package, and it works perfectly with ggplot2. The difference between data frame and table will be explored in my next lecture, in the next talk. Only have in mind that we generally have to manipulate the data. We have to cleaning, to organize the data before do any kind of plot, before go to a descriptive analysis, or before go to a modeling approach. So mapping is another important component in the ggplot2, and this component is a straightforward way to say that we have some variables in the data frame, variables means the columns in the data frame, and then we have these variables in the data set, and each of those variables means something to the plot. In other words, mapping links the variables in the data to the graphical properties. For example, if we have this column of the data representing the x values in the x-axis, while that column represents the values on the y-axis. Another variable can represent the shape, another variable can represent the dot, and sometimes the same variable can represent also the dot and color, or can represent the color of a line, it represents the line type, and so on. With aesthetics, we can also describe the visual characteristics of the final plot. And with the facet mapping, the last topic in this slide, with facet mapping, we can apply the same properties to different panels, where each of those panels represent a subset of the original data. This is a really cool way when you have groups in your data set and you want to show how those groups, what is the relationship between the responsive variable with some covariable given the group, and then you can use these panels, the facets, to do it. This is the first data set we are using to demonstrate how to work with ggplot2. This is a simulated dairy cattle breeding program where the data is comprised of founders with phantom parents, that is represented here by the NA, missing values, and by phenotype the individuals on milk yield. So for each individual, we have information of parents, sex, and herd over 10 generations. And furthermore, each generation is comprised by 1,000 animals, and for each year, 10% of best males are selected, and 500 of best female are selected. But this is just the way we are doing the selection. It's just a small example to be fair. So after read the data using the read RDS function that I'm showing here, and assuming clearly that the data is enough tied to be used as to be used as to do like a descriptive analysis, we can then start our first plot defining which variable we are mapping to be in the x-axis and y-axis. Here we are interested in the relationship between phenotype and year given the sex of the animal. To map this information, we declare the data set is in the ggplot function, and add the aesthetic function, the information of year on X here, and the information of phenotype on Y. And we are also passing to the scale system. We want to add a specific color for each sex. The plot object P cannot be displayed because we don't have any layer in this ggplot yet. And then we have to add some layers, and then we can see how this plot looks like. Another interesting thing is that every ggplot layer specifies one geometry and one statistics transformation, or can specify both. And here we are using this green, this plus sign green, as a way to add new layers to the plot. Thus, every time you need to add a layer, facets, teams, or anything, you should use this plus sign. The ggplot2 was firstly developed to work with layers, and for each layer we had to specify a geometry and a statistical transformation, as I said. In this example, we are adding a layer that includes a point for each pair of Cartesian coordinates between the variables ear and fennel. The stat is equal to identity because this means that we are not applying any statistical transformation to. So now we have our first plot, which shows the phenotype over generation, where for each point, a color is attributed based on the sex of the animal. And in this particular case, we have red for females and green for males. The position is equal to identity. That place each object exactly where in the context of this graphic. For G on point, we generally use it. We generally use the identity because we needed these points exactly where they should be. But we can change the position when working with different plots like histograms. Moreover, all additional parameters in a layer can be passed through the argument params here. In this particular case, we have shape is equal 1, and we are not removing missing data. In this case, we are using shape is equal 1 because we want dots without fill. As I said, we can also include this NA.rm equal to true if you wanted to remove missing data, or false if we not want to remove missing data. In this particular case, our data, there is no missing data in our data. It's just an example of how we can do it. In ggplot, we have sensible defaults for most of the parameters. And for example, we did not pass the value for point size to the plot, and the plot still works because they know that there is a standard plot size for ggplot. And this plot shows, for example, the average of phenotype and seems to be increasing over generation, but apparently there is no difference between sex. Facets, as I said, is the way to divide your plot into multiple panels, where each of those panels will be represented by a subset of your data. This subset can be like a group like sex, and then you have one panel for female, one other panel for male, and each of those panels have a subset of the data related to the sex. The same logic applied for components defining aesthetics are then applied to each of those panels. You only have to make sure the layout of the panels have some meaning to you and some meaning for someone that is reading your plot. In ggplot, we have three types of facets, and as I'm showing here, the face to new, face to wrap, and face to grid. The face to new is the default for a single plot, and you never have to specify like face to new. It's the default for ggplot. While the face to wrap can be used when you have a variable with like n levels, and then you can split those variables with face wrap into 2D ribbon of panels. On the other hand, when we have, for example, two categorical variables, each of these categories with like 3 levels, for example, we can use a row and column system to plot the 2D grid in the way that in the row we can plot one variable with 3 levels, and another in the column we can plot another variable with the 3 levels. This is what the facet grid do for us. We can see the facet grid as a matrix where the levels of one variable is then plotting the rows, and then another is plotting the column. This is a visual representation showing the difference between face-to-wrap and face-to-grid, as discussed previously. The left figure shows a face-to-wrap that we can assume like a variable with 9 levels, and then each level will be described in each of these panels, and then the level 1, level 2, 3, up to level 9. On the other hand, in the left figure, we show, in the right figure, we have the representation of a faced grid. In this case, we can assume we declare a variable with 3 levels in the row and another variable with 3 levels in the column. And the combination of these levels will give me each of these 9 panels. Let me see this in practice. So this is the cattle data. The idea is to illustrate the idea behind face-to-wrap and grid. And here we are interested in see the relationship between the phenotype and the generation. In this case, generation means year, but now plotting it by sex. We are including a layer with point as geometry and splitting the phenotype giving the sex of animal by using the face-to-wrap. And the face-to-wrap argument, the face argument is equal to the variable that we want to split, in this case sex. Now we have an example of face-to-grid, and we are including a layer to describe the points without any statistical transformation, and we are passing the geometry, the shape information, and in the face-to-grid here, we are using this face-to-grid to get the levels of sex in the rows and the levels of herd in the columns, and then where the function vars, this function here, this function vars, is used to link the facet to the variable in the data set. Data does not represent graph properties directly in ggplot. Thus, it is very seldom that you should specify variables in your dataset that can be represented as, for example, shape, position, line type, and so on. If the variable is a factor with n levels, thus we end up with, say, any colors, any discrete colors. On the other hand, if the variable is continuous, then the color should be represented by a gradient of colors. Scales provides the tools that allow you to interpret the plot. For a plot with 2 axes, we must have 2 positions in the scale corresponding to them. Here I am present 4 possible types of position. As you can see here, we have numeric, discrete, binary, and date. For ggplot has some standards. For example, here we have to type the same thing: scale x something, scale y something, and this something can be like continuous, discrete, binary, or date. And I want to explain a bit more about binary and date scales. Binary variable represents the discretization of a continuous variable into bins. As an example, to bin values for age into categories like 20 to 39 years old, 40 to 59 years old, and so on. While date is another special variable in R, and which represents the number of days since 1st January 1970, if I'm not, 1970. And then before this date, we have negative values, and after this date, we have positive values. Clearly, inside of each of these scales, we have arguments that allow us to modify position scales into x and y axis. Same scales also can be modified into the legend output. And here I am showing 4 different types. The scale for fill, color discrete, and color continuous, and color bind. So for fill, we have different colors for fill, and this we have scale fill for grays, scale fill when you have the angle of the color, that means the hue, and scale fill manual that you can include any kind of color you want using, for example, the X code and so on. We can, for example, modify the fill using gray colors and selecting colors for another. Imagine that if we have points and lines, and then we can use gray colors for points, and then select hue colors for lines. We can do it in several ways, manually or not. Other example of scales which modifies legend are line type, shape, and so on, etc. You don't necessarily need to know how scales works to make a plot with ggplot2, because ggplot2 has the standards scales. Here we have an example of how to use these scales in practice. I'm modifying the color scales manually using the hexadecimal color code, the X code. And for green, we have this code. For the red, we have this code. If you wanted to get this kind of code to color your plot, you can go to the Google and type X color, HEX. It will open a color gradient where you can pick any color that suits you, and then you can get the RGB code, the X code, I think the XYZ code too, and then you can use those codes directly to ggplot and get the color that suits. Another simple and standard way to modify colors in ggplot is using packages that has some palettes. And ggplot has this scale color brewer. In this case, I'm using here, I'm updating the last plot, modifying the color, and using the brewer function with palette dark 2 that gives me this green and orange color, for green for female and orange for male. But there are some other packages that you can use for get some palettes of colors, such as the Viridis package, and it's something that you can explore. The general idea of a statistics component in the ggplot is get the raw observation pass through mapping and apply specific statistical methods, statistical transformation to return some new values. And clearly these new values has some meaning to be there. We can use the statistical transformation to calculate, for example, a regression line and plot that regression line in your plot. We can calculate the box plot parameters such as the minimum, median, quantiles, maximum, outliers, and end up with a box plot visualization that represents the distribution of your data with some possible outliers. Here we are showing a linear regression using the orange data, and this is the data I'm using, orange data. We have 3 variables, 3 represented from 1 to 5 individuals. We have age of these trees and circumference. And here we are plotting the circumference against the age, and then we have the layer to get the point plotted, and another layer to plot the line. Here we are using the geom line, and the statistic transformation is the smooth with additional parameters. In this case, the standard for smooth is the lowest method, but here I'm using the linear model method without standard error. And this gives me the linear regression that it represents this overwhelming plus beta times the age of the tree. This data set has 35 rows and 3 columns of records. We can come back now to the cattle breeding program data. Here we have a better example of the cattle data using the box plot to show the phenotype distribution over generation, given the level of herd and sex. This clearly gives us a better view of the data rather than just plot their Cartesian coordinates using dots. The box plot allows us to see if the distribution is or not symmetric, and under normal assumption and with enough observation, we expected something like symmetric, as we can see here, because I'm simulating the phenotype as following a normal distribution, and it's what is expected is that. We can also include different colors for outliers points. In this particular case, the outliers can be seen in red. And how I did it, I used the layer with the box plot, and then statistical transformation equal to boxplot2. And then as additional parameter, I'm including the outlier color as red and outlier shape as 1, and then we have this dot with red color without fill. Basically, to make this plot, we are using a layer with both geom and stat using boxplot method. This is the way that we create this kind of plot. Geometry is the most important component in ggplot, and compared to statistical transformation component, because this is the component people most use in ggplot. Geometry basically takes care on handle with scale and the statistics that came from mapping, and they apply the standard rules defined internally. For example, if we declare a geom box plot automatically, ggplot apply a boxplot statistics transformation without ask you. Clearly, if you want to change the statistic transformation because you did it before in your data manipulation, well, you can do it in ggplot, and then you can modify the statistic component, the stat component operating in the background. In this example, the geom point in the first layer is using the default point color and size, while the layer with geom line, this one, is using the standard line type, size, and color. So here we can see we are adding a facet wrap to map trees as facets. And this allows us to calculate the regression line for each of those trees, the subsets. Each panel here represents a subset, and in this subset we have just information about each of these trees. We can see now that the increasing in the variability show it when we plot just the circumference against the age. You can see that the variance is increasing over age, is now explained by an effect of tree, right? And this is the basic idea of mixed effect models. Actually, we can see now that the increasing the variability shown in the left plot can be explained by this effect of tree, and this changing in the overall mean and the intercept is related to the group effect. For this particular example, we can see that the intercept doesn't vary much, but the slope, yes, the slope is varying a lot bit when we are over the age of those trees. Some trees is increasing their circumference quicker than other trees, and this gave us this amount of variability over time. Just keep in mind, this is the main idea of mixed effect models application. So there are shortcuts function for statistics and geometries, because for up to now we are just seeing layers. We are adding layers to the ggplot, but there is shortcuts that generate the shortcuts that we work, right? Those functions are the most used by our user, and generally few users know about the layer function that we are talking up to now. Here we have an example of different geometries. You can see, you can use to describe the graph you have in mind, basically. You can see different geometries like geonab line to draw a line in the plot, geobar to draw a bar chart, geodensity, geodot plot, and so on. Each geom has a specific statistical transformation predefined by the ggplot, and each statistical transformation has a specific geometry predefined by ggplot. Thus, you can draw a plot using geom something, and you can also draw a plot just using stati something. You can look at more about those geoms and stats by using the help search function, as I did here in this part of the plot, in this part of the slide. Sorry. So now we will see different plots using ggplot. I am starting with the geom density plot for the cattle data. So to build this plot, we should declare the geom density function. In this case, I'm using the aesthetic inside the density rather than declare it in the main part of the plot in the ggplot. What's the difference, right? The difference is everything you include in the ggplot function is a global parameter and will be applying all of your layers. While when you include some specific aesthetics in a specific layer, it is just work for that layer. It will not be hierarchically including another layers. The density plot is really useful to represent the distribution of a continuous variable. However, if you remember, we have the phenotype. In this data set, the phenotype is measured over years. Then maybe the best plot is not just a density plot for the response variable, but in this particular case, we know that the animals have been phenotyped over generation, and probably if we put distribution, a density plot for each year should be much more informative than just a general density plot. We can solve it using the ggRidge package, which allows us to use the geom density ridge and function, and we end up with this plot. So this function draws the density of phenotype by year using the position of year declared in the y-axis. Thus, we can see the shifting of the distribution over the generation. You can see what's happening with the mean and the variance over generation. Here we can clearly see that the mean is shifting from more or less 38 to 55, more or less, while the phenotype variability does not appear to change over time. If you are interested in differences between sex, thus you can add a fixed wrap here, and then you can get the density plot for each year given the sex. Another useful plot to represent the distribution of the numerical data is the histogram I'm showing this plot. It divides the entire range of values into a series of bins, or say intervals, and count the number of points that falls into that interval. To build such kind of plot in ggplot2, we can use the geom histogram, as I'm showing in the left side in here, right? This histogram shows the storm dataset. Each facet represents the absolute frequency of tropical storms over the year. And we can see that most of these events are concentrated between August and October. Here we are adding a Y label and X label that allow us to change the labels of the axis. In this particular case, I'm introducing the theme function, and I am using the axis text x argument because we have to change the angle of these values to make this plot clear. But we will discuss more about this theme in further slides, in next slides. Another way to represent a histogram can be using relative frequency rather than absolute one that I'm showing I will show in the right side. The way to calculate the relative frequency is declaring it on the aesthetics for a y-axis. In this case, we are counting the number of events using the stat count, right? And then we are dividing this stat counting by the total number of events. Thus, y is scaled to be between 0 and 1. So, to transform the scale of y into percentage, we then have to modify the scale position, the position scale of the plot. And how we can do it? We can do it using the scale y continuous, because in this case, the responsive variables is continuous between 0 and 1, and then we can use the scale y continuous with labels equal to percentage using the package scales, and we end up with this plot. This graph shows us that there is an indication that the relative frequency of tropical storms is increased over time, but to be sure, further investigation what happened in the years before the first year in the plot is necessary to make sure that the seasonality is not interfering in our conclusions. Here we come back to the absolute frequency of the tropical storms. However, in this plot we are stacking the mounting frequency of the event by year. Do you remember that we talked about position? Now we change the position from identity to stack, and then we are stacking the frequency per month in each year. We can do that setting the fill to be a factor that depends on the month, and change as I said, the position to stack. There is another kind of plot, the same like histogram, but in this particular case, I am showing you the same information, but using a position equal to fill. We then calculate the proportion of tropical storms per month in a year. Consequently, the y values for each year should be between 0 and 1. The sum of the proportion per month in a year should be 1. These plots make easy to see that months like 8, 9, and 10 have high chance of have tropical storms than the other months compared to the plot of left side. These plots are actually complementary to understand the information, and you never just you should use more than one plot to get all the information from the data, not just one. So I will stop the presentation here, and and because we have more or less 44 minutes now, and I will start in the part 2 of ggplot from the stat summary. See you there.